Okay, it's hunting season. Elmer Fudd has just cornered Daffy Duck up in a tree. So the question is, with the current data in the sample problem, is Elmer Fudd going to hit Daffy, or is Elmer Fudd going to miss? Alright, so we're going to start off, because this is kind of like this is a projectile problem, so I'm going to start off by drawing my vectors. So I'm going to draw a vector right up from the muzzle straight up to where Daffy is, or relatively where Elmer hopes to hit. Now we're going to make the assumption that Elmer is aiming directly at the duck. Okay, so I'll finish drawing my triangle, because pretty much anything that we're doing with vectors is dealing with right triangles. Okay, I finished my triangle. Okay, there we go. So we've got a right triangle. We've got our values. We've got our angle here, which is theta. We've got the muzzle velocity. VI initial is equal to 42.0 meters per second. Okay, Daffy. And let's just go ahead and use delta Y. That's actually not what we're trying to find, but we know that Daffy is exactly 12 meters up in the tree. We know that the tree is 18 meters away, so that's my delta X. Change in horizontal distance. And with all this information, what's going to happen? If Elmer shoots directly at Daffy, is he going to hit the duck, or is the duck going to fall underneath the bullet? Okay, a couple of other little bits and pieces you need to know. We need to know the acceleration due to gravity, and we're going to assume this is on Earth and not some fabled planet the Warner Brothers have developed. So that is 9.81 meters per second squared. In another video, I'll show how none of these values actually matter to the problem, because we can actually solve the problem without resorting to just plugging the numbers in. But right now, I'm going to show you how to solve this problem with the numbers. Okay, so we're going to need to know a couple things. First off, we are dealing with two different types of problem. We're dealing with projectiles launched at an angle, that would be the bullet, and we're also dealing with the vertical motion, or I'm sorry, we're dealing with vertical motion of a projectile that falls from rest. Now, in this case, Daffy Duck has no horizontal velocity. Once Daffy Duck drops, he's just going to drop like, well, a duck. So, the first question that I want to know is, how far is Daffy actually going to drop? So I'm going to define a new delta y of Daffy, and that's one of our unknowns. Okay, we've got a formula that'll work just fine for that. Delta y is equal to 1/2 a sub y times delta t squared. So that is equal to 1/2 a sub y times delta t squared. Okay, so this is what we're trying to find. Or at least that's one of the things that we're trying to find. Now, don't forget, Daffy is 12 meters up. So when we're trying to find delta y of Daffy, we're trying to find how far is Daffy Duck going to drop in the amount of time that he's given. Okay, we'll get to the time in a minute. Let's go on to the next part. We want to know the delta y of the bullet. So as Daffy is dropping, the bullet is going up. But gravity is going to be pulling both Daffy and the bullet down at about the same rate. So my question is, is the bullet going to meet Daffy at some point here? So let's go ahead and define the other equation that we need. Delta y of the bullet. How do you spell it? E-T? Okay, E-T. Okay, delta y of the bullet. And we're going to use the projectiles launched at an angle formula right here. Let's see, here we go, the bottom one. So delta y of the bullet is equal to initial velocity times sine of theta times delta t plus 1/2 AY delta t squared. So if you'll notice, this equation is slightly similar to our other equation. The only difference is the bullet is being launched upward at an angle theta, and Daffy is falling. So in other words, we're trying to find out at the top of the arc, where is this bullet going to end up? I mean, if we didn't have to deal with gravity, the bullet would go in a straight line distance, but because we do have to deal with gravity, the bullet will also drop at the same time. Okay, so what else do we need to know? We have our initial velocity. We have our acceleration due to gravity, but we don't have the time. Also, we do not have the angle, but that should be pretty simple. Again, all we're really using is simple trigonometry. I'll bring up the formula right over here. We're looking at the tangent formula. We have the opposite side. We've got delta y is equal to 12 meters. That's our opposite side. Delta x is equal to 18 meters. That's our adjacent side. Remember, the hypotenuse is always opposite of the right angle in any kind of right triangle. So because we know the opposite and the adjacent side, we want to use the tangent function. Tangent of theta is equal to opposite over adjacent. And because we're looking for theta, we're going to have to take the opposite tangent of tangent -1 of the opposite side, which is 12.0 meters, divided by the adjacent side, which is 18.0 meters. Okay, let's go ahead and plug that in the calculator really quick. 12 divided by 18, so we're looking at 0.6 repeating, get the opposite tangent of that, and let's go ahead and stick with three significant figures, 33.69, which is 33.7 degrees. Okay, so we're good right there. All right, let's go on with the next part. We now know the theta, but we don't know the time. Okay, here's the deal. Elmer Fudd is the one shooting the bullet, and as soon as Elmer Fudd shoots the bullet, Daffy Duck is going to drop. So what we're really looking at for time-wise is how long is it going to take the bullet to go from Elmer Fudd all the way to the tree where Daffy Duck is hanging. Okay, so the distance that you got to travel is 18 meters. So let's go ahead and figure out a formula for that really quick. This is the formula that we want to use for projectiles launched at an angle. Delta x is equal to vi cosine theta delta t. I'll put that up here really quick. Delta x is equal to vi cosine theta times delta t. And because we're looking for the time, we want to divide both sides by vi cosine of theta. So I'm going to change that formula really quick, because whatever you do to one side, you want to do to both sides. And really, the equal sign can be kind of like a pivoted point, so I can just kind of rotate the whole formula and then just divide both sides by vi cosine of theta. Just remember to use your algebra. Okay, so this is going to be delta t is equal to delta x divided by vi cosine of theta. Okay, let's go ahead and plug the numbers in. We know that delta x is equal to 18.0 meters. I'll just plug that in, 18.0 meters, all divided by initial velocity is 42.0 meters per second, and multiply all of that by cosine of theta, which is 33.7 degrees. Okay, so we'll go ahead and plug that into the calculator really quick. So let's see, 18 divided by the quantity of 42 times cosine of 33.7. Remember, on your calculators, you want to make sure you're in degrees. So the amount of time it's going to take is about half a second. We'll go ahead and use three significant figures because we have 3 in all of our values. So that's going to be 0.515 seconds. Okay, so now we've got our angle, we've got our time. Let's go ahead and plug the numbers in. Okay, so the bullet, let's go ahead and deal with the bullet first. That's going to equal to your VI, which is 42.0 meters per second, multiplied by sine of theta, 33.7 degrees, and again multiplied by the time, which is 0.515 seconds. That should give us a nice little distance. Added to, whoops, I forgot, a sub y is actually negative. Remember, you're dropping. Acceleration due to gravity is going to be a negative value. So let's go ahead and plug the rest of that in. That's going to be 1/2, I like using parentheses, times negative 9.81 meters per second squared, multiplied by my time, 0.515 seconds squared. Okay, yeah, I'm kind of running out of room there, but you kind of know that I like to get all the values into the problem first, then just go ahead and plug everything into the calculator. Okay, so let's see. We'll start out with the first part. That is going to be 42 times sine of 33.7 times 0.515 seconds. Okay, so I'm just going to go ahead and separate these two figures out. That is roughly 12.0, and that's going to be in meters. Okay, now let's get the second part of the formula. Sorry about scrunching everything up there. The second part is going to be 1/2 times negative 9.81 times 0.515 squared. And actually, I shouldn't have put a plus in there because that's going to be a negative value, as you can see on the calculator. So that is going to be minus 1.30. I'll go ahead and use 3 sig figs. So 12 minus 1.3 means the bullet is going to rise about 10.7 meters. Okay, so we know what's going to happen to the bullet. From ground zero, it's going to go up to 10.7. Let's go on to the next part, Daffy. Okay, so Daffy, on the other hand, is going to drop, well, we'll have to figure this out. That's 1/2 multiplied by a sub y, which is negative 9.81 meters per second squared, multiplied by the time squared. And let's see, what is the time squared? That is 0.515 seconds squared. And I'm not sure if I even have to put that in the calculator because we already see from here that this part of the equation for Daffy dropping is the exact same as the second half of the equation, and we're going to end up with 1.30 meters. Daffy is going to drop 1.3 meters. Bear in mind, Daffy started at 12. So what's 12.0 meters minus 1.30 meters? 10.7 meters. In other words, if Elmer Fudd aims his gun directly at Daffy, Elmer Fudd will hit the bird.